The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
The weekend is over. Time to get back to business. So, a couple of announcements. Tomorrow we'll have Quiz 4 based on Homework 4. I'll be available from 2:15 to 3:15 under normal office hours. If you can't get in to see me at that time, then just send a note and we'll arrange to meet at some other time. And there's this, actually, Lori has made a sign-up sheet, sort of 5-minute blocks, so that if you do want to come by to look at regrades, you don't have to be hanging around waiting for a long period of time. And if you can't get in during that time, there's no expiry. You can get the grade change at some later date, and we'll make sure we fix things up. So, last day we were talking about covalent bonding, looking at linear combination of atomic orbitals into molecular orbitals, and we saw that there's two types of molecular orbitals involving S and P block elements that are germane to us. We're not going to go into D block in any detail here. At the level of 3091, I think that S and P block teaches you the rudiments, and to go beyond that really requires some intensive quantum mechanics. So we're going to stay with S and P block. And we saw that if we had two atomic S orbitals, when they blended to form the molecular orbital, it took on this sort of ellipsoidal shape. We called that a sigma orbital. And the characteristic of a sigma orbital is that you have continuous electron density from one nucleus to the other. We said no holidays, constant electronic density. We could then combine an S orbital and a P orbital, as, for example, in the case of hydrogen fluoride. In the case of S plus P, we'll end up with an orbital that looks something like this, and it is also termed a sigma orbital, because, again, if you look from one nucleus to the other, there is continuous electron density, no holidays. This sigma orbital is a little bit different in shape from that sigma orbital, but they're both sigmas. And then we saw what could happen with p orbitals, and there's two options here. The first is shown when the two p orbitals meet axially on end. When they meet axially on end, these two lobes smear to give us the lobe shown in this cartoon. Again, continuous electron density from one nucleus to the other. That fits the definition of a sigma orbital. And then something that only the p's can do, when they smear laterally. These lobes smear to give a molecular lobe. These lobes smear to give a molecular lobe. These two lobes collectively comprise one molecular orbital. And the characteristic here is, in contrast to zero holidays, here you have zero density. We have a nodal plane normal to the board. There is no electron density. You can go clear line of sight from one nucleus to the other with zero electron density. And this is called a pi orbital. Pi orbital. And then we went on, we looked at a couple of things like nitrogen, oxygen, and fluorine. But in case of nitrogen and oxygen, we saw that in order to get the triple and double bond, we needed a mix. We needed a mix of sigma orbital and pi orbital. And that's the template. If you're going to make a single bond, you may be able to get away with a sigma. But if you're going to make a multiple bond, a double bond or a triple bond, you're going to have a mix of sigma and pi. And I think that's the way we ended the lecture last day, looking at energy level diagrams. And let's see, what else do we have? Yeah, so we saw this. Here's the end on end. This is a sigma orbital coming from 2p atomic orbitals. And remember the convention. The z-axis is conventionally the axis along which the two atoms bond. And then this is the lateral smearing to give us the pi orbital. And I think I showed you that if you cut this, it looks this way. We went into this, and oh, we just had a great time. So now what I want to do is I want to show that you can extend this business of multiple bonds to hybridized systems. Now, I know Professor Ballinger last week talked about methane. And the way to rationalize methane was to mix S and P atomic orbitals to make a hybridized orbital. And the hybridized orbital that was constructed was the sp3 hybrid. So in order to get the CH4 was explained in terms of the sp3 hybrid orbital. As you recall, carbon in its valence shell has six electrons in total, but 4 valence electrons. And the 4 valence electrons are depicted 2 in the s orbital and 2 in the p orbitals. And clearly that configuration doesn't have the capacity to form 4 bonds. Somehow we've got to generate 4 unpaired electrons, and the sp3 was shown to take one of the s orbitals. This is not a 1s. It's, let's say, it's 1 s orbital and 3 p orbitals. Hence, we get the term sp3, and these are equivalent. And so now, by the Hund rule, I've got 4 unpaired electrons ready to bond. And since there's 4 of them and they're equivalent in energy, we dispose them equivalently in space. So if I want to take a central point and put 4 struts off that central point, symmetrically disposed in space, this will form the struts that go from the center to the vertices of a tetrahedron, and this gives us the 109-degree bond angle. And there's a whole host of compounds that are explained by this bonding configuration. But now let's look at another one. How about this molecule? C2H4. It's known as ethylene. Ethylene, precursor to polyethylene. And let's first of all start with the Lewis structure. Lewis structure, 2 carbons here, and I've got hydrogens. So remember, I'm looking for octet around the carbon, so 1, 2, 3, 4. 4 electrons around the left carbon. Let's bring in an electron from the hydrogen. That way the hydrogen is isoelectronic with helium. We'll bring an electron from the other hydrogen. So this is isoelectronic with helium. And now carbon has 2, 4, 6. And if it could pick up 2 electrons from the right carbon, it's in business. And the right-handed carbon mimics the left-handed carbon. And so hydrogen each donates an electron. And now let's check. The left carbon has 2, 4, 6, 8. So it's octet stable. The right carbon, 2, 4, 6, 8. It's octet stable. And the way to explain this is there's some kind of a double bond here. So let's draw the double bond. And for now, we'll put the hydrogens later on. We'll get to the point where when we see carbon and a strut, we'll assume that the default setting is, if I don't write anything at the end of the strut, assume that it means that there's hydrogen. And here's something to always look for. When you see a carbon, check to see there's 4 struts off the carbon. If you don't have 4 struts off the carbon, start looking. There's probably something missing. Okay? So now how are we going to explain this? We've got a double bond. We already know a double bond, there's a tip off there. That means we need a sigma and a pi. But with 4 struts, 109 degrees apart, there's no way you can form a double bond. So this isn't going to work. The sp3 hybridization will not work. But maybe there's something else we can do if we want to make a double bond. If we want to make a double bond, what we could do perhaps is to start with that same box structure. And what's the gambit here? What I want to do is I want to save an unhybridized p orbital, because the p orbital is your friend. Because only with a p orbital do you have the capacity to smear laterally. And if you don't have the capacity to smear laterally, you can't make a pi bond. So let's do something here, but not burn all the p orbitals. So how about doing this? Instead of making 4, what if I make 3 and save one of the p's? So this is p, it's unhybridized, and these are hybridized. So I'm going to take one of an s, the only s I've got, and I'm only going to take 2 of the p's. So I'll call this sp2 hybridized. So I got sp2 and p. Now let's go through the geometric rules. If I have 3 struts symmetrically disposed, because these are equivalent energies, if they're symmetrically disposed in space, they're going to describe, first they're going to lie in a plane, and they're going to be 120 degrees apart, lying in a plane. That's what this tells me. Now I got the 4th one out here, and where's the 4th one going to be? It can be normal to the plane. So I've got 3 sp2s lying in a plane, and I've got an unhybridized p out of the plane. Hey, this is starting to look good, because what I could do is start bringing these together, and maybe make something work. So here's another sketch of what this looks like. You can see the three sp2 orbitals lying in a plane, and then above and below this rather bloated dumbbell shape, p orbital. And there's the top view. All right? Now, here's two of them opposing one another. Right? They're opposing one another. So if these are the carbons, I could take these two sp2 orbitals, blend them, and I could make a sigma orbital. And now what? I've still got these unhybridized p orbitals. I can bring those in, and they'll smear top and bottom, and now I've got a pi orbital. A sigma and a pi gives me my double bond. So by hybridizing sp2, I can give rise to the setting that will allow the formation of the double bond. So there it is. There's the sigma is in the center here, sp2 plus sp2, and then the pi's give me the double bond. And remember, the two lobes together constitute a single pi bond. So that's great. So we're just going to bring these two in. So we'll take sp2 plus sp2 axially. Axially will give a sigma bond, and then p plus p laterally will give the pi bond, and together this is the double bond. And then the other sp2s are hanging off the end, and they each pick up a hydrogen. So I can draw this molecule instead of this format that I've drawn here. I could really draw it in the following manner. Here's carbon-carbon, and then show these as sort of, I'm trying to give the idea that this is a 120-degree angle, and I'm going to leave the hydrogens off because you're a sophisticated audience. I told you once, I don't have to tell you again. So there it is. There's ethylene. And just for grins and chuckles, you might want to see how to do one more form of hybridization. If you want to do a really good job of welding, you need a very, very energy-intensive fuel. Use acetylene. Acetylene. Acetylene is C2H2. It's known as acetylene. And if you go through the Lewis structure, you'll conclude that you've got a triple bond there. And we already saw last day, the triple bond in nitrogen was almost 1 megajoule per mole. So there's a lot of energy in here. So you got your acetylene torch and your oxygen feed. You're going to do a lot of, I said you need 4 struts, so what's that? There's a hydrogen, and triple bond in the center. How are you going to make a triple bond? Well, let's leave 2 unmixed p orbitals. So then instead of having one just up and down, I could have one up and down and one in and out of the board. And I can form a double bond, and what's left over, and you can go through and rationalize that this would require sp hybridization. Sp plus unmixed p orbitals. This p smears with its neighbor to give a pi. This p smears with its neighbor to give a pi. And this smears axially to give a sigma. So 1 sigma plus 2 pi's, triple bond. That's the whole story. Cool. All right. So what are we learning here? There's a paradigm here, and that is that covalent bonds, a couple of characteristics that I want you to know. First of all, they're saturated. Remember I said that ionic bonds are unsaturated, and you say, well, okay, don't tell me what they aren't, tell me what they are. Well, what they aren't is in contrast to what these are. So now I can finish the story. What does it mean they're saturated? Once you put an electron from the hydrogen and an electron from the carbon into the orbital, that's the end of the story. We've taken care of business here. There's no revisiting the situation, unlike in the case of the ionic compounds where the positive attracts a negative, but it has the capacity to attract yet another negative, and the field is felt attenuating, of course, but it is palpable out to infinity. So we say that the ionic bonds are unsaturated, the covalent bonds are saturated. Once you've got 2 electrons in the orbital, move on. The second thing is, what you're seeing here is that they are directional. They're directional. That is to say, in the case of sp3, they're 109 degrees apart off the central carbon. That's the only hook on which you can hang another atom. So if you make methane, if you make carbon tetrachloride, if you make freon, they're all going to be the same shape molecule, tetrahedral. because the struts come off the central carbon. Look at this. Anything that gives me sp2 hybridization is going to be what? What's the shape of that molecule? It lies in a plane. It's planar. That's what it means to lie in a plane, doesn't it? And look at the shape. They're always 120 degrees apart. So this means that there's a relationship between the directionality of the bond and the shape of the molecule. And why are the bonds directional in the first place? Because of electronic structure. This is the theme of 3091. It's going to be echoed over and over again. The electronic structure dictates everything. It's just dominoes after this, once you understand electronic structure. We did all of this for one reason, to achieve octet stability. That's the, you know, if I peel away the board and I look in behind here, there's two words, octet stability. That's the only thing that's going on here. This system will do anything to achieve octet stability. It's savage. It just does anything, okay? All right. All right, so now what I want to do is I want to make this the proposal that the electronic structure will dictate the shape of all molecules. So let's put up a grand system, and that's what I want to do. I'll put that up and work through it. Oh, here's some more cartoons. This is taken from another book. So you see the pi bond here, and here's the sigma bond from the two sp2s, and then the remaining sp2s. This is supposed to indicate that this is coming out at you, but this does not give me the sense of 120 degrees. This is crummy art, but really, this is really crummy. I'm taking that down. It's horrible. All right, so now this is what I've put up. This is the rules for determining molecular shape, and in our text, it's known as electron domain theory. If your classmates down the hall in 511.1 and 511.2, instead of electron domain, it's the same idea, but they use a different term. Instead of electron domain theory, they call it VSEPR, which is called VESPER, so that they can pronounce it. VESPER, which stands for valence shell electron pair repulsion. Electron pair repulsion. And all of this will come clear in about the next 15 minutes. It'll start all making sense. So here's a set of rules. I generated these. This isn't in the book. And all of this will be posted by mid-afternoon. So you can take it down if you want, or you can just take it off the web in a little bit. All right, so I want to go through and illustrate how this is used. And so what I want to do is I want to use this in order to deduce, to infer the molecular architecture of three molecules. So let's start with this series, SF6, BRF5, and IF4 minus. So these are three molecules, and I would say, okay, tell me what the shapes of these molecules what will it be? So let's start with SF6. SF6 is interesting. We're going to have some of that in the class later on when I teach diffusion. SF6 is a very large molecule. It's very heavy. Molecular weight is about 150 grams per mole. Its density is 5 times that of air. But its main claim to fame is that it's chemically rather inert, and so it's used extensively in the metal casting industry. If you look under the hood of the car and you see aluminum castings, magnesium castings for things like water pump housing and so on, those castings were made under the protection of a blanket of sulfur hexafluoride. Because as we already know, aluminum and magnesium are really good metals, and they will react violently with oxygen in the air. So you have to, when you're pouring molten aluminum, you've got to keep the oxygen in the air away from it, and they use SF6. You could say, well, we could use a liquid flux, but what if some of the liquid flux gets entrained in the casting? Then the casting becomes weak, the wheel cracks, there's a collision, maybe people lose their lives, people are sued. So it's better to use a gas phase shield. Okay, but the bad news is the SF bond, which you can calculate the energy for right now using the Pauling formula, sits smack dab in the middle of the, just off visible. And so this is a fantastic infrared absorber. And this stuff goes up into the upper atmosphere and has a greenhouse gas coefficient that is phenomenal. And so the industry is under pressure to get rid of this. So if somebody in here wants to do something good for the environment and allow us to continue to make castings of aluminum and magnesium and reduce the mass of the vehicles, but do so in a way that doesn't damage the upper atmosphere, you know, this is the trade-off. You know, somebody in this room will be sitting in policy someday. And what's the simple solution? If I come and tell you that the greenhouse gas coefficient of SF6 is 12,000 times that of CO2, what would you do? Say, well, let's just ban it. All right? Well, that's dumb, okay? That's really dumb because now we don't have aluminum and magnesium castings, and so now the mass of the automobiles go up. So what would an MIT person do? An MIT person would say, well, let's figure out what's the tailpipe emission trade-off to cleaning the atmosphere by not allowing SF6 to go into the atmosphere. See, you got to know some chemistry, otherwise you just make dumb decisions. All right? That having been said, I wonder what the structure of this molecule is. Okay, so first thing we do is Lewis structure. Let's write the Lewis structure. So I'm going to put sulfur in here, and sulfur's got 6 valence electrons. It's got 6 valence electrons, right? Sulfur is 2s2, 2p4. And so let's bring up a fluorine. Fluorine's got 7 valence electrons, so there's 1, 2, 3, 4, 5, 6, 7. So now fluorine, by sharing 1 electron with sulfur, becomes octet stable, and we can keep doing this. I'm not going to put all of these down. I'm just going to put a single electron from each fluorine. You'll know that there's more like this, and here's another fluorine. Here's another fluorine. Here's another fluorine. And here's another fluorine. So this is great. All the fluorines are octet stable. Now let's see what's going on with sulfur. It's got 2, 4, 6, 8, 10, 12. 12. It's got 12 electrons. That's some octet with 12, isn't it? Okay. Well, let me tell you something. With some of the very electronegative elements that have a very, very high average valence electron energies, they can form, and the ones that are in the dark blue are elements that on occasion can form expanded octets. These are called expanded octets. And the expanded octet is an attempt, you know, if octet stability is good and I have a huge appetite for electrons, I just might try to pull in a few more. So it happens, and let's look at the energy level diagram of that. You know, here's my 2s, and here's my 2p. So this is 1, 2, 3, 4, 5, 6. There's my 6 valence electrons, right? But here, what do I have? I need to be able to form 6 pairs of bonds. So I need to hybridize. The best I can do is hybridize sp3. That'll give me 4. I need to get more. You know where I'm going to go? I'm going to go to the orbital store. And where's the orbital store? It's over here. D. D. You know, you say, well, wait a minute. What are you talking about? We're going to bring down the Ds, okay? We'll bring down the Ds, and here's how we do it. There's 1, 2, 3. If I grab 2 of these Ds and I mix S's, P's, and these 2 D's, that can give me this configuration. sp3, and I'm taking 2 of the D's. sp3, 2D, and then I've got 3 D's left here unmixed. So now, Hund Rule, 6 electrons. 1, 2, 3, 4, 5, 6. So this is how one can hybridize in order to allow for expanded octet. All right? And also account for the bonds that we're forming here. All right, so this is called electron domain theory. Each one of these orbitals here, each one of these orbitals that has electron occupancy around the center atom, each one of these is termed an electron domain. An electron domain. And there's 2 types of electron domains. Those that involve bonds and those that do not involve bonds. So the 6 that I've circled are bonding domains. So these are all bonding domains. And for example, this one here, which I'll put a square around, it's off to the side. It's a non-bonding domain. It doesn't get involved in bonding, but it's not even part of the central atom. Okay, so we'll see that in a second. All right, so I've got 6 electron domains, and now I want to put up the skeletal structure. So if I have my central sulfur here, how can I put 6 domains symmetrically in space? The way I do that is I make essentially this triple cross that constitutes the coordinate system, right? X, Y, and Z. This gives me 6 domains in symmetric disposition around a central atom. And in this case, So 6 electron domains implies octahedral skeleton. Octahedral skeleton. Skeleton of what? It's the skeleton of the molecule. It's where the electrons can reside. And why is this called octahedral? This is, you look at this, if you were to link these up in the plane, so you link up 4 in the plane and then build a pyramid to the top, can you see that the pyramid to the top has 4 faces to it? So 4 faces on the up, 4 faces on the down, 4 plus 4 is 8, so octahedral, 8-faced. But I look at that and I see the 6 struts, and I do this cognitive discordance when I'm saying it's octahedral, but I'm seeing 6. But you just get used to it. So this is octahedral, and clearly we can put the fluorines at the ends of the struts. So there's SF6. That's the shape of the molecule. That's the shape of the molecule because we have 6 bonding domains. All the domains are engaged in bonding, so they're all the same. There's no distinction between them. So we have an octahedral skeleton, and in this case we have an octahedral molecule. Octahedral molecule. Let's see, what else can we say about it? Oh, polar or nonpolar? What do you think? As soon as you see fluorine, you know, it's just like in the Manchurian Candidate. When someone says fluorine, you go, electronegative, most electronegative, right? So, bingo, this is really super electronegative. So we know this is a very polar bond. But, as I showed you last day, there's 6 symmetrically disposed polar bonds, so it's a nonpolar molecule. Terrific. All right, let's go on. This is fun. Let's do the next one. Let's do bromine pentafluoride. Bromine pentafluoride. Okay. Now look at BRF5. So according to this, whoops, let's go back to our rules here. Write the Lewis structure. Now it'll give us electron distribution. So here's bromine, and it's got 1, 2, 3, 4, 5, 6, 7. And each fluorine is going to come up same as last time. Each fluorine will share 1 electron with bromine. So that'll give fluorine its octet. It's 2, 4, 6, 8. And then I'm going to do the same. There's the fluorine. 1, 2, 3. Another fluorine. Another fluorine. Another fluorine. So I got 1, 2, 3, 4, 5. And then I got a pair of electrons that are hanging around. So bromine has shared one each of 5 of its electrons with the fluorine, and then there's a pair here that is unshared. Okay, so first of all, let's count the number of electron domains around the central bromine. So I got 1, 2, 3, 4, 5, 6. 6 electron domains. All right, so, but we're not panicking now because we know that expanded octets exist and it's okay. All right, but there's a difference here. There's a difference. So first of all, 6 electron domains. So that means, again, octahedral skeleton. Octahedral skeleton. So the electrons and the bonds are going to be in this kind of a formation again with the bromine in the center. But there's one little distinction here, and that is that they're not all bonding domains. You see, this pair over here is not involved in any bonding. So I've got 5 bonding domains. 5 bonding domains, and 1 non-bonding. 1 non-bonding domain. Okay, so the 5 are in the oval, and the 1 is in the rectangle here. All right, and sometimes if you look in some old chemistry books, non-bonding is one of these strange. It's clear it's a latecomer to the language. Sometimes people call these lone pairs. They're lone pairs. They're both electrons come from the central atom, and they haven't gotten picked up for any kind of duty. So they're alone. They're lone pairs. All right, so now let's take a look at the shape of the molecule. The shape of the molecule, it turns out that it doesn't really matter. There's a symmetry here, right? It doesn't matter if I have the 5 fluorines in the plane and above, or the 5 fluorines underneath and the lone pair up here. Those are symmetric. One's just upside down from the other. There's nothing distinguishable. So just to get this thing over with, I'm going to put the fluorines in the plane. Okay, so this is the This is the XY plane, and then the Z direction is up here, and then this is the non-bonding pair is off to one side here. So you don't see the electrons. If you try to detect the shape of this molecule, you simply see the atoms. So you'll see bromine in the center, and you'll see 5 fluorines about it. And what's going to be the shape of this thing? Well, 4 of the fluorines lie in a plane, and then the 5th fluorine lies above the plane, dead center, over the bromine. So I can pitch a tent here, and what am I going to have? I'm going to have something that's square-based and a pyramid. So the molecule is square pyramidal. Square pyramidal molecule. The structure is still octahedral for the electrons, but the molecule, square pyramidal molecule. What else can we say about this? Oh, how about, is this polar or nonpolar? It's polar. You can see there's asymmetry here. There's extra electrons down on the bottom, the way I've drawn it. So that means that I could model this as a dipole with the bottom part of it negative and the top part of it positive, net neutral, or we could draw it this way. I think we were going to put an arrow pointing in the direction of the negative end of the dipole. So that's good. Wow, we're clicking. Now there's a piece of paper down here. It's got more information on it. Let's get this one. So I'm going to do, let's do one more. This is so much fun. Let's do IF4. IF4, tetrafluoroiodate. IF4, it's a complex ion. All right, so we're going to do the same thing. We'll write the Lewis structure. And iodine 1, 2, 3, 4, 5, 6, 7. Okay, so here's fluorine. 1, 2, 3, 4, 5, 6, 7. So by sharing one electron with iodine, fluorine becomes octet stable. So this one will do it as well. You know, I've got enough room here. I think I'm going to go for the gold. I'm going to put all the electrons here. So there's fluorine over here. Here's fluorine. So there's 8 there. And let's put another fluorine up here. I'm going to move that. I'm going to move this just a little bit. I'm going to raise this. Put this off to the side, IF4 minus. I'll put a fluorine here. 1, 2, 3, 4, 5, 6, 7. So there's the 4 fluorines. And now let's look at the electrons around iodine. I gave 1, 2, 3, 4, 5, 6, 7. But you see, this thing's net negative. Where did the net negative come from? How does something become net negative? It acquires an electron through electron transfer. This is really cool because this is covalent bonding within something that is engaged in electron transfer. So to make this thing, this complex ion net negative, means that I had to throw one more electron in here into the mix. And where is it going to go? Where do electrons live? They live in orbitals. And there is one orbital that's just waiting for it right here. So I'm going to put this electron in here. So now what do I have? I've got 1, 2, 3, 4 bonding orbitals. 4 orbitals where I have one electron from the iodine and one electron from the fluorine. So let's write that down. 4 bonding domains. And I'm still talking about the central iodine. Here's 2 of its electrons that had no place to go. So that's one lone pair. Here's the 7th electron. No place to go, and then the net negative charge is an electron, and it's sitting in this. So there's 2 non-bonding domains. 2 non-bonding domains for a total of 6. So this means 6 electron domains, so that means octahedral skeleton again. Now, question, where do I put the fluorines? Well, you say, yeah, put them at the end somewhere. So there's 2 possibilities now, unlike the other case. See, I've got this possibility. This is door number 1. This is door number 1. I put the fluorines in the plane. Okay? And door number 2, it's the same electron structure. I'll put the fluorines above and below, and then I'll put the electron pairs next to one another. These are distinguishable. Agreed? So, what's it tell you is, it says number 3 is maximize separation between domains. Number 4, give more space to non-bonding domains. Non-bonding domains. Let's think about the physics behind that. Why? Electrons that are in non-bonding domains are sitting there with no interaction with a nucleus. Whereas the ones that are in bonding domains, they're on this axis. See, I've got 2 electrons sitting in here, but they're scrunched in between nuclei. Whereas these 2 are just hanging out there, negative, just brandishing this negative charge. You see? And here's another negative charge. So what is it going to try to do? It's going to try to get as far apart as possible. So that's why that rule is there, number 4. So which of these 2 configurations keeps these farther apart from one another? Door number 1 or door number 2? Number 1. One's up here, one's up here. These 2 are too close together. So this is not what happens. And in fact, this is the structure of tetrafluoroiodate. So what do we see? All we see is the atoms. The iodine, the 4 fluorines, they lie in a plane. And what's the top view of this thing? It's just a simple regular cross. So you have fluorines at 4 corners of a square, iodine in the center. This is called square planar. This is a square planar molecule. Square planar molecule. Polar or nonpolar? It's nonpolar. This is cool. Look, it's net negative, but it's nonpolar. So that means that even though it has a net negative charge, if I get really far away, how do I model that thing? How do I model it? When I get really far away, this is what it looks like. Point charge, negative. See, way out here. I don't know. I don't care what the internal structure looks like. I don't care about the electron, because it's all symmetric anyways. It's very, very good. All right, so let's look at one more. This is too much fun. This is too much fun. All right, so these all had, but so what's the punchline of this one here? You see we had 3, SF6, BRF5, IF4 minus. They all had octahedral skeletons, but the molecular architecture was different because of the relative number of bonding and non-bonding domains. But they all started with octahedral skeleton. Now I'm going to do something else. Now I'm going to compare this series that have the same formula. The same formula. So let's do 3 tetrafluorides. CF4, SF4, and tetrafluoroiodate. See, they all have it's F4. And I'm going to show you 3 different things. Well, what's this one? You know this one in your head. This is tetrahedral, right? This one here, I just write it by inspection. Boom, 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 boom. That's done. Finished. Polar, nonpolar, fluorine, strongly electronegative, but symmetric bonds, nonpolar. And this one we just did. So if your memory's good, you know that this one's square planar. Okay? Now, so let's do SF4. What's SF4 looks like? What does it look like? It looks something like this. We start with the Lewis structure. That's what it says up there. So sulfur, 1, 2, 3, 4, 5, 6. And fluorines, I'm going to put F, 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 and F. Actually, I know what's coming. I'm going to put the F over here. So there's 7 fluorine electrons from the fluorine, and then the 1 from the sulfur makes 8. So we have a bonding domain here, octet stability, and likewise the same will happen here, here, and here. So what do we have? 2, 4, 6, 8, and 2 of the electrons from the sulfur are not involved in bonding, so they constitute a non-bonding pair. So I've got 2, 4, 6, 8, 10. I've got 10 bonding, 10 electrons, or let's say 5 electron domains. There's 5 electron domains here. That's different. See, here, there's 4 electron domains. Here, there's 6 electron domains. 4 ED, and they're all bonding, and 4 bonding. Here is 6 ED and 4 bonding. And this is 5 ED, 5 electron domains, 4 bonding. Gee, they're all tetrafluoride, and I've just proved that if you have 4 fluorines, you got 4 bonds. This is really consistent. It's not terribly deep, but anyways, okay, so here we are. Here we are. No, it's important that at the end of the day, you know, these things rationalize. Okay, so we've got 4 bonding and 1 non-bonding. 1 non-bonding. So how do I take, if I have a central atom here, how do I put 5 struts off it equally spaced? So that's going to mean 1, 2, 3 in the plane, one above and one below. That's 5. Okay? So this is called, the 5 struts, this is called Trigonal Bipyramid. And how do they get that? If you look at the plane, you can join the 3 in the plane. This is 120 degrees, agreed? If I'm looking down on this plane. And now what I can do is I can make a pyramid here, but this is a pyramid that has 3 faces. So I've got, this is called a trigonal pyramid. This is a trigonal pyramid, but this would have above and below, so it's a trigonal bipyramid. Trigonal bipyramid. That's a fancy name for something that's got 5 struts sticking out of a simple atom. Okay? Trigonal bipyramid. So now, what are we going to do? We're going to now put the fluorines. So we've got 2 choices again. We've got sulfur in the center. 1, 2, 3, 4, 5. So here's one possibility, is to put the non-bonding electrons in the plane with the other fluorines. This is called the equatorial position. If you think of this as the globe, okay, there's North Pole, South Pole, and these 3 lie at the equator. So this is called the equatorial position. This is equatorial. So that's one possibility. The other possibility is to put the lone pair either at the North Pole or the South Pole. And if we use the same idea as before, in other words, we try to minimize the interaction between the unpaired electrons, excuse me, the non-bonding electrons and other atoms, which one is going to give this less contact with its neighbors, door number 1 or door number 2? See, this one has, actually your book even shows a little cartoon for this. See, if you put it at equatorial position, it's got 2, if you like, 2 nearest fluorines. Okay? Whereas if you put it at a polar location, it's got 3 nearest fluorines. So if we use that, this is called polar. By that analysis, door number 1 should be a minimal interaction, and in fact, that was one of the things that we were told to do. You see, place non-bonding domains. This is rule number 5. Non-bonding domains at equatorial positions in a trigonal bipyramid. That's what you say if someone asks you to say something, into a microphone. Just say that. Okay. And so that means the molecule is going to look like this. And this molecule is called seesaw or teeter-totter, because you don't see the non-bonding pair here. Your characterization apparatus would find fluorine, sulfur, fluorine, and then these 2 are underneath like a sawhorse at 120 degrees. And how about, is this polar or non-polar? This is polar because I've got electrons over here, so I could model this as a dipole or in this fashion. Okay. So this has been really good. Let's see, what else we have here? So far I've been doing this with heteronuclear molecules. But we can do this with homonuclear molecules. So I want to show you two conditions. Look at sp3, and I will look at sp2. All right, I'm going to work with carbon alone, no hydrogen. So sp3, I start with a central carbon, sp3 hybridized, and carbon goes everywhere. So each carbon has 4 nearest neighbors, and they're all at 109 degrees, and they all have the same strut length, the same bond length. 1, 2, 3, 4, and so on. Carbon here, carbon up here, and these are going in and out of the board. But I think you can see that one thing is certain. There will be regular arrays in 3 dimensions. Regular arrays. Regular 3D array. And if you look at this from a distance, what you'll find is this is forming the diamond cubic crystal structure. Diamond cubic crystal structure. In this instance, carbon is hybridized sp3. And the consequence of that is diamond cubic. Now, if carbon instead hybridizes as sp2, we know that we have 3 bonds identical lying in the plane. So let's do that one. So here's carbon, 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 carbon. And then this one has 1, 2, and 3 over to here. Okay? And what are we seeing here? We're seeing a hexagonal pattern, aren't we? This is just 3 of the bonds, but I said, look, remember, you got to keep me honest here. Look at this carbon. How many sticks off of the carbon? 1, 2, 3. I told you we better have 4. We better have 4. And I only got 3. So what happened? Where's the last stick? Well, I've taken this configuration over here, all right, S and P, and I've mixed them to get sp2. That means there must be some p orbital here somewhere. And where is it? Well, it's sitting right here. There's a p orbital here, and 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 a p orbital here, and a p orbital here, and so on and so on and so on. And it turns out that the bond length is such that these p orbitals are able to bond cooperatively. Okay? And so they form p bonds are cooperative. And they're so cooperative that the electrons are not associated with any particular bond. We say that the electrons are delocalized. And we'll see a little bit more of that later, but you might as well learn it now. They're delocalized. This is the structure of graphite. This is the structure of graphite. And what do we have here? We have strong covalent bonds in the plane, and then we have these weak delocalized bonds normal to the plane. So the planes can slide over one another, which is what gives graphite its lubricity. That's why you squirt graphite powder into a lock in the wintertime to give it some lubrication. So these glide over one another, and furthermore, it's not only lubricity, you get electronic conduction, and graphite has a mildly decent electronic conductivity. Unlike diamond, where all of the electrons are tightly bound, very tightly bound. And by the way, these bonds are very, very strong. The planes, the bonds in the plane of graphite are extremely strong. But plane to plane, they glide. Okay, so you can think of these almost diamond-like rafts in terms of the bond strength. But these are flat, and these are three-dimensional. The other thing that happens is you have really, really tight bonds. What's this optical properties here? This one is transparent to visible light. Why? Because electrons are tightly bound. So you've got this really weak photon, visible light, 2 electron volt photon comes in, and it can't excite anything, but the bonds are so strong that it's refracted. So one of the properties of this is a very high refractive index. Very high refractive index. Whereas here, electronic conduction means it's got very, very low excitation, and hence graphite is an absorber. It appears black because any light that shines on it is absorbed. See, everything comes from the electronic properties. You can explain that it's lubricity, and you can explain its electronic conduction, and you can explain its absorption of photons. Now, I mentioned electronics here and the impact on photonics, you see. High index of refraction, this is socially a very dangerous quantity. Because what happens is, this is what makes diamond so precious. It's not just that it's rare, it's how it functions in society. It takes a small amount of diamond. You know, you're sitting, you're just minding your own business. You just went out, you just want to have a drink, you're sitting there. There's some gal sitting over in the corner of this dimly lit cafe. She's got a diamond stud on. That diamond stud takes a tiny, tiny amount of lumens, and thanks to this insidious property, concentrates them, and then shoots them across, catches your eye, and then the trouble starts. Okay? So this sp3 hybridized carbon is very dangerous owing to this property. Now, I draw your attention to the periodic table. You know, it may happen that some of you are going to feel compelled to make a long-term commitment to another person and initiate that commitment with the presentation of a stone typically made of diamond. Well, I draw your attention to the fact that at room temperature, the stable form of carbon is graphite. Now, I want you to think about this. If you want to present a ring that contains the stone that's symbolic of eternal love, Doesn't it make sense to present the stable form, not the metastable form? I mean, I was just thinking about this, but so my point is that this is the stable form. I've done my part to explain it in terms of sp2 hybridization. I leave it up to you to explain it to your sweetheart. Okay, you have a nice day.